All right, connecting cities with minimum cost. So we have n cities or n nodes, and we have a bunch of connections between those nodes. Or you could think of the connections as like edges. So a connection would be an edge between, say, x and y with some cost or some edge weight. And they want us to return the weight of the minimum spanning tree to connect these cities. So you could think of like we essentially just want to find the minimum weight edges and sum that up to actually connect the cities together. Okay. Um, so we're going to use Kruskall's algorithm, and the first thing we do in Kruskall's algorithm is we sort the edges. So we're going to do arrays.sort connections. I misspelled that. Pass in a comparator, AB, and do A2 because index 2 is the cost. Subtract that from the other connections cost, and this will put it in ascending order. Cool. And my spacing's off. Why is it off? Okay, cool. And now we need to do union find. So what do we? So we're going to do an efficient union find. So we're going to do we're going to create a parent array, and we're also going to create a rank array. And this should be a size of, we're going to do n plus 1. And you'll see in a second why it's not n. It just makes the code convenient and just simpler. But yeah, you'll see in a second. So I'm going to do int I equals 1. I is less than or equal to n plus I. So we need to make, in union find, the first thing that we do is we set the parent of every node to itself. So parent of I just equals I. Okay, cool. And now we just need to loop through our connections. So for every, or our edges. So for every connection and connections, so I'm gonna have union. When I write this union method, it's going to connect two cities together. Like if it'll take this connection, grab the two nodes out of connection, and it'll put those two nodes together. But if they're already connected, union will just return false. So just keep that in mind. This union, if the nodes are already connected, it'll return false. If they're not connected, it'll connect them and return true. Okay. So we're going to pass in our parent array, pass in the rank, and pass in the two nodes. So that'll be connection 0 and connection 1. Okay. And if we're able to union, then we need to sum up the cost of this edge. So int cost equals 0. Yeah, so this will be cost plus equals connection 2 because index 2 is the cost. And eventually we should have n minus 1 edges because it takes n minus 1 edges to connect n nodes. So we need to keep track of our number of edges because if we're not able to hit n minus 1 edges, if we don't end up with n minus 1 edges, then that means that the graph is actually disconnected and it's not actually possible to connect all the cities, so we should return -1. So after a successful union, we're going to increment the number of edges, and let's say we connect all n nodes. Eventually, let's say there's like a bunch of connections, right? Like there's a lot of extra edges, more edges than nodes. Then what'll happen is once we've connected all the edges, all the nodes, this union will just return false. So num edges will only ever hit n minus 1. That's the most it could ever be. Okay, so what we're going to do is return that we want to return the cost, but only if num edges is equal to n minus 1. So if num edges equals n minus 1, then return the cost. Otherwise, return -1. Okay, so this is pretty much done. We just have to write the union and the find method. So let's do that really quick. So private boolean union int parent int rank, and then pass in the two nodes. Cool. And the first thing we do is grab the representatives or the roots of the nodes x and y. So we'll do int root x equals parent, or not parent, find, pass in parent, and then pass in x. Okay, cool. So we grab the root of x by using the find method. Then we do the same thing with y. Cool. And now we just check if, and I'll write the find method in a second, but we'll just finish the union for now. So if the rank, or sorry, so first we got to check, are these in the same set? So if root x is equal to root y, so that means that they are already connected. So if they're already connected, then just return false. There, we already put them together. So we don't need we don't want this edge. Yeah, so we don't want to union this. So essentially we don't want this edge here because we already connected these two nodes. So yeah, if they're already connected, just return false. And if they're not connected, well then we need to check which has the bigger rank, because whoever has the bigger rank, we want to make that, we want that to be the root, and we want the smaller tree, the tree with the smaller rank needs to be put into the larger tree. So rank of root x, if the rank of root x is greater than the rank of root y, then we want to make the parent of root y equal to root x. So you could think of like the rank as the height, because in the beginning rank does represent the height of each like tree essentially. But after the compression, the rank will change. But anyway, the rank won't change, but the height will change. So it doesn't necessarily represent the rank, but it does in the beginning. But for now, you can just think of it like as the height. So if the height of this tree is greater than the height of this tree, then put the smaller tree as a child of the root of the bigger tree. Okay. And now we want to do the opposite. So if root y's tree is bigger, or if it's taller, or its height is bigger, whatever, then we just do parent of root x equals root y. Okay, cool. And if they're, say the ranks are equal, then we could just arbitrarily pick one of the nodes, or one of the trees to be the we could arbitrarily pick one of the nodes to be the root of the other tree. So we're just going to do copy paste this one right here. It doesn't matter which one we pick though. And because they're equal, that means you could think of like their height, the height of this guy just increased because we made the if they're equal in height, and like if this tree is the height, has the same height as this tree, but we make it, if we attach it to the root of this tree, well then this root x just increased in height by 1. So we're going to increase the rank of root x. Okay. So now we just return true because we connected the nodes. We just have to write the find method now and we're done. So, and that's really short. So private int find int parent, pass in x. Okay, and we're going to say, how do I want to do this? So if we already found the parent, so let's say if parent x equals x, then just return x. So we're going to do this recursively. So this is our base case. So we found the root because the parent of x is equal to x. So just return it. And otherwise, recurse up the tree. So like just keep going up the parent. So we're just passing in the parent of x as into this. And so this will just keep going up the tree looking for the root of the tree. And what we want to do, since we're doing compression here, we want to say parent of x equals the result. So let me explain this after I fix. Okay, so what this is going to do is is going to keep recursing until it finds the root. So once it finds the root, it's going to return the root here. And we're going to assign that root. And once we go back through the recursion, we're going to assign the root to as the parent of all the nodes that were in the branch, in this branch, as we were going from the leaf node all the way up to the root. So now basically from the leaf node and all the nodes in between, all of their parents will be set to this root here. So that's essentially the compression in this union find. Okay, so now I think we're done. Let's just run it. Let's see, did I make any mistakes? I did. 55. What's wrong with this? Oh, I didn't actually return the parent x here. Okay, so once we find the root here and we assign the root to all the parents, we need to just return that root. So that'll be parent x here. Okay, so now let's run it. Cool. Let's use the example test cases. So far, so good. Let's submit it. Cool, and it works. So yeah, so this is pretty efficient. Yeah, so the time complexity ends up being n log n, or like if the number of connections is n. Or sorry, so if let's actually, okay, it's actually, we'll call connections, say it's e for edges. So this would be e log e for sorting right here, right? And the if we're going through all the connections here, this would be like an O of E operation. So again, E is the number of edges or number of connections. And union is going to be a log n operation. The reason it's a log n and not O of n operation, because normally it's an O of n operation, but because of this ranking that we did here, we're always attaching the smaller tree into the bigger tree. So in the worst case, you kind of end up with like a balanced tree almost. Although it's not balanced because of the compression that we do, but essentially it ends up being, at the end of the day, this is just a log n operation. So this is O of E times log E. So this is E log E. Okay, so the whole thing ends up being E log E. So yeah, that's it for this problem. If you like the video, you can give it a thumbs up. You can subscribe if you want. Cool, bye.